Waste CO2 diffuses from the cells into the bloodstream, and a small amount, about 10%, remains in solution in the plasma and extracellular fluid matrix. Another 10% combines with the hemoglobin, but most of the waste CO2 that enters the bloodstream combines with water to form carbonic acid. But don't worry, the carbonic acid is almost immediately dissociated into the bicarbonate anion and a proton. Most of the CO2 created as the waste byproduct of cellular metabolism is transported in the bloodstream in the form of the bicarbonate anion. The vast network of venules and veins collect CO2-laden blood from the body into progressively larger vessels culminating in the vena cava. From there, the heart pumps it into the pulmonary arteries, and in the lungs, the CO2 is offloaded to the atmosphere in exchange for oxygen. Oxygen delivery and carbon dioxide removal are intrinsically linked. You may remember the oxygen-hemoglobin dissociation curve. This is nothing more than a graph displaying the proportion of hemoglobin in its saturated or oxygen-laden form on the vertical axis against the partial pressure of oxygen on the horizontal axis. It makes sense that if we increase the partial pressure of oxygen, the proportion of hemoglobin that is saturated also increases. If we choose an arbitrary value for the partial pressure of oxygen on the x-axis and draw a line up to the curve, we can determine the corresponding proportion of saturated hemoglobin. If we choose a second arbitrary point on the x-axis with a higher partial pressure of oxygen and draw a similar line, we not surprisingly see that the proportion of saturated hemoglobin is also higher. The insight from this curve and the reason that we study it is that there are conditions such as temperature, pH, and the partial pressure of CO2 that affect the affinity of hemoglobin for oxygen. When these conditions change, they're said to shift the curve to the left or to the right. Depending on how the ambient conditions have changed and affected the affinity of the hemoglobin, we may find that there is more or less saturated hemoglobin at the same partial pressures of oxygen that we had already investigated. The Bohr effect is a direct result of a shift in the curve. The Bohr effect describes how the relatively high partial pressure of carbon dioxide in the peripheral tissues causes a right shift in the oxygen-hemoglobin dissociation curve and, consequently, increased dissociation of oxygen. In other words, when the blood loaded with oxygen gets to the peripheral tissues and encounters the higher concentration of CO2 there, the high CO2 causes more oxygen to separate from the blood cells and be available to the tissue. Conversely, when the carbon dioxide-laden blood reaches the lungs, the high partial pressure of oxygen increases the saturation of hemoglobin without directly causing a left shift in the oxyhemoglobin dissociation curve. The Haldane effect is the result of the increasing saturation. Oxygen-saturated hemoglobin is much less accommodating to the CO2 molecules, and the carbon dioxide becomes more likely to detach and diffuse into the alveoli for exhalation. Of course, if circulation is compromised, then none of this happens and CO2 accumulates in the tissues without ever reaching the lungs to be eliminated.